Nowadays, almost no one uses assembler to write a whole PC application, including a graphical user interface. An assembler is used to implement efficient computation algorithms and is integrated with software solutions written in high-level languages such as C#, C++, Java, and even Python. Naturally, writing code in assembler is bound to some particular processor architecture, and without a compilation, it is usually not portable across different platforms, unlike many high-level language solutions. Writing computationally demanding algorithms in assembler enables pushing hardware to its limit, using all its features and writing efficient and compact code in terms of energy, performance, and size. With the cost of complexity, you obtain absolute control over the hardware. Merging assembler code and a high-level programming solution is demanding. While assembler code is native code running on the particular CPU, some high-level framework, such as C# provide developers with numerous automation features. Just to mention, perhaps the most important one is automated memory management. Those features may become a nightmare for assembler developer, however, if not properly handled. There are also different rules regarding operating systems and architectures. Before we go deeper into the specific cases, let's introduce two general methods of integrating assembler code with an application written in a high-level language. Static merging, where assembler code is compiled and merged with the executable part of the application. Merging of all components, including assembler binary objects, is performed during the compilation and linking phase of development. Assembler code is loaded into memory during program execution. It provides faster access to the assembler code during the first call to the function, better compatibility, but lower flexibility for updates. An update requires recompiling the entire solution, including the high-level language application. Dynamic merging, where assembler code is kept separate as a library, for example, a DLL file under a Windows operating system, and is loaded on demand by the application written in the high-level language during runtime. Assembler code is loaded into memory only prior to the call to the assembler code and is really kept in a separate file. It enables independent exchange of assembler code and libraries without recompiling the high-level application. On the other hand, it is error-prone. Improper changes to the assembler code, such as changes to the interface, can easily break high-level applications. Further updates may also cause incompatibility. Windows is one of the dominating operating systems. Historically, most applications were written in unmanaged C++. There are significant differences between development and assembler integration of 32-bit and 64-bit code. In particular, it concerns calling conventions that differ significantly between 32-bit and 64-bit function calls. Assembler code is always compiled to unmanaged code, and thus integration with the code written in a high-level language that uses virtualization frameworks, such as .NET, requires code proxying, which is specific to the framework and follows strict rules regarding memory management. Dynamic memory allocation is common in high-level languages, and it is an indispensable part of object-oriented programming, whether it is C++ and native code or C# and managed code. In any case, the Windows operating system managed memory and controls access to the memory blocks. At the assembler level, dynamic memory management is troublesome and requires operating system level functions, which in turn involves Windows API calls. It is very inconvenient, so a common programming pattern is to allocate memory in the high-level part and pass it to the assembler code. Assembler code is commonly stateless and performs atomic operations on data passed from the calling application. It is possible to write a simple Windows command line application purely in assembler. Interfacing with the user is handled via the operating system API, and assembler code must call Windows functions, for example, to draw text, pop up a message box, and so on. While it is possible to build a Windows command line application purely in assembler, there is usually no reason to implement such a solution, beyond practicing Windows API calls in assembler, which, on the other hand, is quite useful for further development. With a high-level language application is compiled to unmanaged code, integration gets quite simple. Calling an assembler code doesn't significantly differ from calling any other library. The assembler code is compiled to a DLL library and is located in a separate file. Assembler functions are exposed via a definition file and exported so that the calling high-level language application knows their prototypes. The assembler library is then loaded into the memory, and any assembler function type is defined in this example via typecasting. Here we present sample code that dynamically loads the assembler dll.dll library using the operating system level load library method. Then our code calls a dummy assembler function named myasm4x and displays the returned value on the command line. The function myasm4x is referenced by its address, dynamically established based on its name. Note that proper handling of a dynamic library loading also involves explicit library unloading, which requires a call to the freeLibraryOS method. Integration with managed code follows the same process as with unmanaged code, but requires following special rules to avoid troublesome memory errors. Managed environments use automated memory management and optimization, such as garbage collector in .NET Framework. The garbage collector runs in parallel with all other applications and automatically traces all references to dynamically allocated objects, freeing the memory when it finds that there are no more references to them. The second task of a garbage collector is a performance optimization. It instantly relocates objects, which involves updating of the reference as object changes their address in memory. It works fine as long as all references are made from managed code. When a pointer is passed as an argument to unmanaged code in assembler, the garbage collector can no longer see the reference and thus can free the memory or relocate it without notifying or updating the reference in the assembler. This raises memory access errors on the operating system level, and it's very troublesome to debug and handle because memory allocation and reallocation done by the garbage collector is run asynchronously, and thus errors do not always occur and seem to be random. For this reason, it is very important to follow the strict rules. 1. Code convention section calling unmanaged code should be marked as unsafe. 2. And each argument passed to the assembler code should be marked as fixed, as in this example. There are no significant differences in general approach to integrating assembler and high-level language written code between Linux and Windows. In any case, you need to follow calling conventions that differ significantly between those operating systems, and code is not straightforwardly portable even at the source code level.